Okay, uh, good evening to all and welcome to the week 9 of problem solving session for the NPTEL course Heat Transfer with course ID noc24-ch17. I hope I am audible now. There was some issue with my audio earlier, so the presentation got just a little bit delayed. My name is Nitish V and I will be your teaching assistant for today. With that, I will move on to this week's problem solving session. Okay. Uh, this was week 9, and for this week we had 5 lectures spanning from lecture 41 to till lecture 45. The lectures had topics on condensation as well as some introduction to the radiation heat transfer. The first lecture for this week, that was lecture 41, was on condensation. Condensation process and different modes of condensation were presented in detail in this lecture, and model equations for the film condensation was discussed by the professor. In the subsequent lecture, that was lecture 42, the remaining part of condensation heat transfer was discussed. In this lecture, correlations for finding heat transfer coefficient for film condensation along plane wall cylindrical geometry, all those were presented and discussed. Lectures 41 and 42 were talking about condensation heat transfer, whereas the next 3 lectures, that was 43, 44 and 45, discussed about radiative heat transfer. Lecture 43 was about an introduction to radiation. An introduction to radiation mode of heat transfer was discussed in detail in this lecture, and the mechanism governing radiation from different materials and dependence of radiation on the intensity and direction was also presented in this lecture. In the subsequent lecture, that was lecture 44, the spectral intensity of radiation was discussed. Intensity, which quantifies the radiation and associated properties, were discussed. Several other related definitions were also introduced during this lecture. In the last lecture for the week, that was lecture 45, the spectral properties of radiation was discussed. Also, an introduction to the Blackbody radiation was also given. More definitions were introduced in this lecture, and Blackbody and its properties were discussed in detail in this lecture, and Planck's law was also presented. So these were the 5 topics that we had for this week. It was about condensation and some introduction to radiation. So it is expected that everyone has gone through these 5 lectures before coming to today's problem solving session, because we will be covering about 4 or 5 different problems spanning these topics. With that, I will begin today's problem solving session, and I will go to the first problem now. Okay, this is problem 1. I will read out the problem statement for you. A vertical plate 500 millimeters high and 200 millimeters wide is to be used to condense saturated steam at 1 atmospheric pressure. At what surface temperature must the plate be maintained to achieve a condensation rate of 25 kilograms per hour? This much is the problem statement. Just go through the problem statement once, and after that we will see what all data is given to us and how we can proceed to solve this problem. Okay, so what we have is a vertical plate. So a vertical plate on which some condensation is happening with a condensation boundary layer. Okay, the plate is having a length of 500 millimeters and a width of say 200 millimeters. Okay, saturated steam is being condensed on one of the surfaces, and we need to find out the surface temperature for this, so that the condensation rate of 25 kilograms per hour can be achieved. Okay, this is the problem statement that we have. Now let's see how we can solve this problem. Okay, before solving, we have been given the properties. We have been given what all the properties of water vapor at 1 atmospheric pressure and a saturation temperature of 100 degrees Celsius. The enthalpy of evaporation or the latent heat is given to us in units of kilojoules per kilogram. And for the water in liquid phase at a film temperature of roughly 360, this is Kelvin, 360 Kelvin, the density in the liquid phase, the specific heat in the liquid phase, the dynamic viscosity, thermal conductivity, and the kinematic viscosity are given to us. With this much data, we need to find out what temperature the plate should be kept at, so that we can achieve a mass flow rate of 25 kilogram per hour for the condensation of saturated stream. Okay. Take a minute to grasp the question. After that, we will discuss the solution methodology. Okay, let's analyze the situation what is given to us. Say this is the plate on which condensation is happening, which is kept say at a temperature of Ts, and there is steam at a temperature of T saturation, and condensation is happening on the surface. That is the scenario that we have. So the total heat transfer that happens in this condensation process, I can write it as Q is equal to mass flow rate of the condensate multiplied by the latent heat. Note that this will not be the latent heat as it is, this will be a corrected latent heat. I will talk about this in a few minutes. Give me a moment, let me change the layout. Okay, so this is the definition for heat transfer, the mass flow rate of the condenser into the corrected latent heat. Or further, this can also be expressed as an average heat transfer coefficient based on the length multiplied the area available for heat transfer multiplied by the temperature difference, just Newton's law. Since saturation temperature is the highest temperature here, it can be expressed in this way also. Now this is an expression for heat transfer rate. From this, what we can do is we can express this all these expressions in terms of mass flow rate, because that is given to us, and that is what our primary based on mass flow rate we have to design our surface temperature. So let me express mass flow rate as just Q divided by corrected latent heat, or this can also be expressed as, since Q is equal to, we know that Q is equal to H bar L, the average convection coefficient, multiplied by area available for heat transfer into T saturation minus the surface temperature divided by corrected latent heat. Okay, this is the expression that we have. Now let me just write it without this term. Mass flow rate is equal to H bar A T saturation minus Ts divided by h bar fg. Okay, among this, now this is our governing, this is the equation that we can start with. This is an equation for the mass flow rate for this particular condensation mechanism. In this problem, the mass flow rate is given to us, mass flow rate is known to us, and the area that is available for heat transfer, the length and width of the plate is known to us, so area is known to us. Saturation temperature is given, it is water vapor that is given to us, and saturation temperature is 100 degrees Celsius. Ts is something that we have to find out at the end of the problem, and we have the corrected latent heat. The corrected latent heat is the correction for actual latent heat accounting for the heat that is taken by the condensed sensible heat that is being taken by the condensed steam. The expression for corrected latent heat is given by the latent heat multiplied by 1 plus 0.68 into a number called non-dimensional number called Jacob's number. This Jacob's number is actually the ratio of sensible heat to the latent heat, and it is given by Cp of liquid, Cp in the liquid phase multiplied by the temperature difference, that is the sensible heat, divided by the latent heat. So let's check here. Cp of liquid we know, saturation temperature we know, Ts is something that we have to find out, and the latent heat is also given to us. So HFG we can calculate once we know Ts. So at the end, not HFG, the corrected HFG. So at the end, only Ts is the unknown in this whole equation. Not only Ts, we don't know the average convection coefficient also. So if we know the average convection coefficient, we can calculate the surface temperature from that quantity. So whatever Jaxi explained is also given here in the problem, that is the mass flow rate is given by heat transfer rate divided by corrected latent heat, and the heat transfer rate can be expressed as HA delta T, and the latent heat is also, corrected latent heat is also divided by this Q to get the mass flow rate, and the corrected latent heat is given by multiplication of the actual latent heat with some factor of Jacobian number, and not Jacobian number, Jacob's number, and Jacob's number is defined as the ratio of sensible heat to latent heat. With this much quantity, with this much knowledge, we can proceed. Now we know that first we need to find out this H bar L, then only we can find out the surface temperature that we need. Okay, this is what we know till now. Any questions till this point?
No, sir, please don't.
Okay. So we know that first we need to find out the convection coefficient. Now this is a problem of flat plate, condensation over a flat plate, vertical flat plate. For that, we know three Nusselt number correlations given for different Reynolds numbers. We know that Reynolds number dictates the type of flow in these cases, and we have three different Reynolds number correlations corresponding to three ranges of Reynolds numbers. First one is for the laminar regime, that is Reynolds number of inside the boundary layer, okay, because there is no Reynolds number outside the boundary layer in condensation cases. This is a flat plate in a quiescent medium, so there is fluid flow only inside the boundary layer. Now this is for the laminar regime, and this is for the transition regime, and this is for the turbulent regime. Three Nusselt number correlations. So first we have to decide on which of these correlations we need to use. For that we obviously need to calculate this Reynolds number for the given boundary length. And the expression we have for Reynolds number is, it is given to us here. Reynolds number is given by 4 times mass flow rate of the condensate divided by dynamic viscosity of the liquid into width of the plate. This is the expression for Reynolds number. So if I substitute that, what I will get is 4 times mass flow rate is 25 kilogram per hour, that is 25 kilogram per 3600 seconds, divided by these quantities, dynamic viscosity, and the width of the plate is 200 millimeters, that I will write as 0.2 meters, and the dynamic viscosity in the liquid phase is given by 324 into 10 power minus 6 Newton second per meter square. 324 into 10 power minus 6. So if we evaluate this quantity, we will get the Reynolds number for the current problem, current scenario. So let me quickly calculate this value, or you can also calculate with me. 4 into 25, 3600, 324 into 10 power minus 6 divided by 0.2. The value that we get is for 28.66 for Reynolds number. Are you getting the same value? Okay, the value that we are getting for the Reynolds number is 428.66. So with that we can go to our Nusselt number correlations, and we see that our Reynolds number value falls in this range. It is not purely laminar, it is a laminar wavy, a transition to the turbulent regime. So this is the Nusselt number correlation that we need to use. So let me rewrite it here. So from this we can get the heat transfer coefficient, average heat transfer coefficient. Let me write an expression for the average heat transfer coefficient. H bar L equal to, let me take the thermal conductivity of the liquid on the other side, and this BL square by G all power 1 by 3. This is an equivalent length scale for this condensation problem over a flat plate. Not BL, UL, that is the kinematic viscosity, UL square by G. So if you take the units, it will come to be in meters. All power 1 by 3 into Reynolds number divided by 1.08 Reynolds number for the boundary layer, or 1.22 minus 5.2. Okay, so let's get the values. Thermal conductivity in the liquid phase is 0.674, and kinematic viscosity is 3.35 into 10 power minus 7. 0.674 0.674 3.35 into 10 power minus 7. First we need to square this quantity, square of the kinematic viscosity, divided by G, take it as 9.8 meters per second square, and take a cube root of this, multiplied by Reynolds number that we just calculated, 428.66 divided by 1.08 times Reynolds number for 28.66 or 1.22 minus 5.2. This, if you evaluate this expression, we will get the value for our average heat transfer coefficient. Let's quickly calculate that. 0.674. If someone has already done, just let me know the value. Divided by 1.08 into 428.66 power 1.22 minus 5.2 into 3.35 into 10 power minus 7 . Has someone already got the value? .8 1/3 okay. So I think we are getting a value of around 7319.85. with the units of watts per meter square Kelvin. Okay, I hope till this point it is clear for everyone. So we wanted to see how much should be the surface temperature for this flat plate, so that the mass flow rate of the condensate would be 25 kilogram per hour. So now that we have found heat transfer a convection coefficient, let us proceed to solve the problem further. Now we know convection coefficient, so the only thing we need to that is left to find out is the Ts. So let me rewrite the expression for the expression for the total heat transfer rate that we wrote earlier. It would be m dot equal to h bar into A into T saturated minus T surface divided by h dash Fg. Okay, this was the expression, and here itself we told that the expression for corrected latent heat was, let me write the numerator as it is, this is the latent heat multiplied by 1 plus 0.68 into Jacob's number, right? And Jacob's number, we said it is given by Cp of the liquid multiplied by T saturation, temperature of saturation minus temperature of the surface divided by HFG. This is what we had. Okay, now I substituted everything in this, and now we see that the T saturation temperature minus surface temperature is appearing in two places. So let's do some rearrangements so that we can express the whole quantity in terms of T saturation minus surface temperature. So if we multiply and expand, we can write it as m dot into HFG, this T sat minus Ts I am taking on one side. Saturation temperature minus surface temperature is equal to this m dot I will multiply with HFG, mass flow rate of the condensate into latent heat divided by this H bar A that we have from here, plus now this quantity 0.68 times mass flow rate into Cp of the liquid into this HFG, and this HFG will get cancelled out at T sat minus Ts term would again appear here, that is this term, all divided by this H bar A term. Okay, is that clear for everyone, or is there something that I missed? Oh, okay. This, no, it is correct. Let me cross check. T sat minus Ts equal to mass times Cp. Okay, is it clear for everyone till this point?
Yes, sir.
Okay, so let me express the whole expression in terms of saturation temperature minus surface temperature. That I can write to be saturation temperature minus surface temperature is equal to mass flow rate into HFG divided by H bar A minus 0.68. I am just skipping one step in between this. You can clearly see how we came to this point. Cp of liquid. What I am doing is I am taking this quantity on the other side, and I am taking these two common, like this H bar A will get multiplied by this T sat minus Ts, that will come here, and that will be here, this term, and that will be this term, this coefficient of T sat minus Ts we will have to minus from that quantity, so that finally we will get this expression. Now in this expression, saturation temperature is known to us 100 degrees Celsius. Okay, 100 degrees Celsius, and or let's find out this quantity itself. What is T sat minus Ts? Mass flow rate is known to us 25 kilogram per hour, 25 by 3600 multiplied by what was HFG? HFG was, the latent heat was given to us as 2257 kilojoules per kilogram. 2257 into 10 power 3. Okay, divided by the heat transfer coefficient that we just found out. That was how much? 7319.85. 7319.85 multiplied by the area available for heat transfer. Remember that it was a vertical plate with a length of 0.5 meters and width of 0.2 meters. So area available for heat transfer is one side. We are taking one side, 0.5 into 0.2, and what will quantity do we get? 0.68 minus 0.68 into mass flow rate, again 25 by 3600, that is the desired mass flow rate that we need, into the Cp in the liquid phase. That should also be given to us. Cp of water in the liquid phase 4203 joules per kilogram Kelvin. Okay, This is the expression for Tsat minus Ts, and if you evaluate, we will get the temperature difference that is expected between saturation temperature and the surface temperature for to achieve the desired mass flow rate. Let me know if these steps are clear.
Yes, sir.
Okay.
Answer is 22.00.
22, the Tsat, yes, 22 degrees, right?
Yes, sir.
Okay, 22.0001 degrees Celsius, 00 something. Okay, this is the temperature difference that you are getting. From that, we can get the desired surface temperature, right? That is Tsat minus 22.01 equal to 77.99, right? This is the desired surface temperature, so that we can obtain a condensation of 25 kilograms per hour. So I think, yeah, that was just from the temperature difference we are finding out the temperature of the plate. Just go through the question again and see whatever the solution strategy that we adopted makes sense or not. Just take a minute to go through the question again and let me know if there is any queries. Is it clear?
Yes, sir.
Okay, then I will move on to the next problem for the day. Problem 2. In the first problem, we saw condensation along a vertical flat plate. Now let's see what we have in this problem. Let me read out the problem for you. The condenser of a steam power plant consists of square inline array of 625 tubes, each of diameter 25 millimeters. Say, assume there are like an array of tubes like this. Array of tubes, 625 of them. Consider conditions for which saturated steam enters at 0.105 bars. Saturated steam is entering at some pressure and condenses on the outer surface of each tube, while a tube wall temperature of 70 degrees Celsius is maintained by the flow of cooling water through the tubes. So the surface temperature for each of these tubes is maintained by flowing some water through these tubes, and the surface temperature of each of these tube walls is 17 degrees Celsius. Determine H bar D. Determine the average convection coefficient. Okay, this is what we have. Go through the first paragraph of the question. And after that we will see what all data we have and how we can proceed to solve this problem. Okay, the difference from previous problem was that in the previous problem steam was condensing along the surface of a flat plate, so we had to vertical flat plate, so we had to go for the find out the Nusselt number correlation, appropriate Nusselt number correlation for that scenario. In this case, steam condensation is on the surface of horizontal cylinders kept in line, and for that again we have to find out the average convection coefficient, just like how we found in the last case. Or the only difference is that in this case we have more number of cylinders, not a single tube. We have many tubes. So for that purpose, we have been given the properties of saturated vapor at that specified temperature. So note that saturation temperature is different from what we saw earlier, and we have been given the properties of saturated liquid at film temperature of 32 degrees Celsius. Okay, different properties are given, like the density in the vapor phase, density in the liquid phase, dynamic viscosity in the liquid phase, Cp in the liquid phase, thermal conductivity in the liquid phase, and the latent heat values. Also, these two expressions we have already seen. The expression for one, the corrected latent heat, that is H dash Fg equal to Hfg multiplied by 1 plus 0.68 times Jacobs number, where Jacobs number is defined as a ratio of sensible heat to latent heat given by Cp of the liquid multiplied by the temperature difference divided by the latent heat. These quantities are given to us, and we have to find out the averaged heat transfer coefficient. This is the problem statement. Take a minute to go through the problem. After that, we will start the solution. We will solve the problem.
Sir. Yes, sir.
Okay. Then we will go ahead and solve the problem. The Nusselt number correlation that we have for laminar flow over a cylinder is given by this expression. And in this, what all values do we? This is the Nusselt number. This is the average heat transfer coefficient that we need to find out. This is diameter of the cylinder. This is thermal conductivity in the liquid phase. C is a coefficient that is given as 0.73729 for condensation on cylindrical surface, and C is equal to 0.826 for condensation on spherical surface. So we will take C as 0.729, and the values rho L is the density in the liquid phase, rho B is the density in the vapor phase, that is given to us. G is 9.8 meters per second square. D is the diameter of the cylinder. This is dynamic viscosity, thermal conductivity, saturation temperature of the vapor, and surface temperature of the cylinder. All these values are known to us, and what we need to find out is this corrected latent heat term, which is given by this expression. So Jacobs number we will find out first, which is given as the ratio of sensible heat to latent heat. So Jacobs number would be, Cp of the liquid multiplied by saturation temperature minus surface temperature divided by Hfg. If I had written mass flow rate, it would cancel out from both sides, so you can ignore that. From this calculation, just find out Jacobs number first. Cp of the liquid is, Cp in the liquid phase is 4178 joules per kilogram Kelvin. 4178 multiplied by saturation temperature in the vapor phase is given to us as 320 Kelvin or 47 degrees Celsius. 47 degrees Celsius minus surface temperature, we are told that it is maintained at 17 degrees Celsius, divided by the latent heat. The latent heat is given to us as 2390 kilojoules per kilogram Kelvin. Okay, let's find out the Jacobs number first. 4178 into 30 divided by 23901. 0.052. The answer that we are getting is for Jacob number is value that we are getting for Jacob number is 0.052. It is a dimensionless quantity, so there is no unit. And if I substitute that in this expression, I will get the corrected latent heat as the sensible latent heat, that is 2390 000 joules per kilogram Kelvin multiplied by 1 plus 0.8 into 0.052. This quantity we will get as
2.47, sir. 2.474.
2.474. I'm getting
No, sir. ये बहुत ज़्यादा है. 2474510.4.
2474
2474.
2390 into 1 plus 0.68 into 0.052. 24745, right? Yeah.
Correct, sir. Correct.
Yes. Two four seven four point something kilojoules per kilogram Kelvin, right? Okay, this is the value that you are getting. Okay, now we have all the values to substitute in this expression, and we can directly substitute them and get the value for h bar d. Okay, before that we see that this corrected heat transfer rate, it is more than the HFG, that was the latent heat was 2390, right? Latent heat was 2390 kilojoules per kilogram Kelvin, and we see that the corrected latent heat is given by 2474 kilojoules per kilogram Kelvin. As I mentioned in the beginning, this corrected latent heat accounts for the sensible heat that is taken by the condensate film also. That is why the value is higher than the latent heat. In addition to latent heat, there is another heat quantity that is going to heat the film, the condensed film. So that part is also added to this latent heat, some sensible part, and that is called the corrected latent heat. With all these inputs, we can now finally calculate the h bar. So h bar, we can substitute all the values in this expression. I think we have all the values, and we can get h bar d. If you want to substitute yourself and find out, you can do that, or else I already have the values. I think it is direct simply substitution. The diameter we know, I think it is a 25 mm diameter tube. Thermal conductivity in the liquid phase is known to us. It is 0.620 watts per meter Kelvin. Density in the liquid and vapor phase are known to us. They are respectively 990 per kilogram per meter cube and 0.0713 kilogram per meter cube. G is 9.8. The corrected latent heat we just found out. Diameter 25 mm, that we already know. Thermal conductivity we already saw. Saturation temperature and surface temperature, I think we just saw that, yes, 47 degrees Celsius and 17 degrees Celsius. And the dynamic viscosity value, that is also known to us as 769 into 10 power minus 6 Newton seconds per meter square. So if you substitute all these values, what we actually get is, okay, let me you you should get somewhere around 7200. The value might be slightly different from what you get. You should get somewhere around this value. Watts per meter square Kelvin. It should be somewhere around 7000. So the value that we are getting is actually the average heat transfer coefficient only for the first tube, that is the top tube, right? But in our case we have an array of tubes arranged one after another in a vertical fashion. So if you want to find out the heat transfer coefficient for the total heat transfer coefficient for such a system, we can do this with an expression given by h bar d equal to h bar d of n equal to the average heat transfer coefficient for the top cylinder multiplied by the number of cylinders to a power factor of n, where n is given by empirical relations to be minus 1.6 minus 1 by 6, sorry. So we can go ahead to calculate the heat transfer coefficient taking into account all these cylindrical tubes. That will be 7275 into multiplied by how many tubes we have. We have, I think, an array of 625 tubes. 625 to the power minus 1 by 6. So if you calculate, you will get this value to be somewhere around 2500. That is what I am getting. Okay, we can see that when we are talking about only the heat transfer coefficient for only the one cylinder, that is the topmost cylinder, it was a high value, but when we were averaging this heat transfer coefficient for all these tubes, the value reduced. The reason for that, can someone guess the reason for that? It is just that the film thickness, the condensed paper film thickness, gets accumulated as we go down base, and it is resulting in a reduction in the heat transport coefficient. That is what is happening. So this is the general expression. Is it the equation for n array of tubes? Yes. This is the equation for n array of tubes, where the h bar d is the average heat transfer coefficient only for the top tube. This is h bar d, and capital N is the number of tubes, and small n is an empirical factor that was determined to be minus 1 by 6. Yes, this is an expression for average heat transfer coefficient when we have condensation over an array of horizontal tubes. We haven't come across, but I went through the lectures. There is one lecture in which professor was giving Nusselt number correlation for horizontal tube, and in that lecture itself he was saying if we have n array of tubes, this quantity will get just multiplied by a factor of n, right? In that case he is taking n as minus 1 by 4. Actually there are two possible values for the small n. One is an experimentally determined value and one is an analytically determined value, but the researchers have been finding that this experimentally determined value is coming closer to, when we determine using this experimental value of small n, we are getting values closer to what we actually measure. So that is why I went forward this n is equal to minus 1 by 6, but in class sir didn't express this expression as it is, but instead he just, professor was just plugging in this capital N, the number of tubes, capital N quantity, somewhere inside this correlation expression itself. I think that might be in, I don't remember it, if it was lecture 44, no sorry, it was the second lecture in condensation, maybe lecture 42 I think. Professor was not explaining this equation, but instead he expressed from the textbook I am referring, it is suggested that minus 1 by 6 is giving more accuracy. So I would say go for minus 1 by 6. Minus 1 by 6 is actually an empirically determined value, so you can choose that for your calculations. Okay. So yeah, that was what was asked in the problem, and we found out the average heat transfer coefficient for such an array of tubes. Let me go back to the problem statement again. Take a minute to go through the problem and let me know if there is something that was not clear in the solution method that we followed. In the first problem, it was condensation on a vertical flat plate, and in the second problem, it is condensation on horizontal tubes, tubes of cylindrical geometry. For cylindrical geometry and spherical geometry, the only difference would be that factor of C, as we saw in this slide. For cylindrical geometry, you have to take the C to be 0.729. And for spherical geometry, the C value would be 0.826. With this Nusselt number correlation, we can find out the average heat transfer coefficient. The only additional thing that we had to evaluate was the corrected latent heat, according for the sensible heat that was taken by the condensed film layer. That was about this problem. Any questions on this problem?
No, sir.
Okay. HFG dash H dash FG can also be taken as H dash FG can also be taken as HFG plus 0.68 CPL. That is what we wrote, right? No, okay. Wait. So you are saying H dash FG can be written as HFG plus 0.68 Cp of liquid into, this is what you are suggesting, right? But no, the correct expression is HFG into 1 plus 0.68 Cp of liquid into Tsat minus Ts. So when we expand that, it will be so when we expand that expression, it will be both are not same, you missed one bracket or missed one HFG. So when you expand this, what you get is HFG plus HFG into 0.68 Cp of liquid into Tsat minus Ts. You open the bracket, but when you open the bracket you did not include this HFG term. Sorry, yes, right. Instead of this, yeah, you are right. Let me correct myself. HFG into 1 plus 0.68 into Jacob's number, right? And Jacob's number equal to Cp of liquid into Tsat minus Ts by yeah, I am writing it again and again, but yeah, you are right. Let me write it on a new page and erase it. HFG into 1 plus 0.68 Jacob's number, which can be written as HFG into 1 plus 0.68 Cp of liquid into, yeah, here I got confused. Here I just forgot this divided by HFG term, which is given by, which can be rewritten as HFG plus 0.68 into Cp of liquid into Tsat minus, this is not Tsat, this is Ts. Yes, whatever you said is right. You can directly substitute Jacobian number here and rewrite the expression. Yeah, I'm sorry for the mistake that I said earlier. You are right. Yeah, thank you. So I hope problem 2 was clear for everyone, right? So shall I proceed to problem 3? Yes. This is problem 3. Let me read out the problem statement. Saturated steam at 0.1 bar condenses with a convection coefficient of 6800 watts per meter square Kelvin on the outside of a brass tube having inner and outer diameters of 16.5 millimeters and 19 millimeters respectively. The convection coefficient for water flowing inside the tube is 5200 watts per meter square Kelvin. Estimate the steam condensation rate per unit length of the tube when the mean temperature is 30 degrees Celsius. If T surface outer temperature is 313 Kelvin and Cp of liquid is, some properties are given. Okay, just read this problem statement. After that we will first discuss the problem statement and then we'll see what is given to us, and then we will see how we can solve that. Okay, there is saturated steam at a specific pressure which is condensing with a convection coefficient of 6800 watts per meter square Kelvin on the outside of a brass tube. Okay, say this is a brass tube with this shaded region showing the tube thickness and this open region showing the inside of the tube, and let this be the outside portion of the tube where steam is condensing with a non-convection coefficient of 6800 watts per meter square Kelvin. Okay, the outer diameter of the tube is given and the inner diameter of the tube the inner diameter and the outer diameter of the tube are given, and we know that there is water flowing inside the tube, and the convection coefficient associated with this water flow is 5200 watts per meter square Kelvin. Okay, now what we have to estimate is the steam condensation rate per unit length of the tube when the mean temperature of the fluid is 30 degrees Celsius, surface temperature is 313 Kelvin, and Cp in the liquid phase is 4.79 joules per kilogram Kelvin. This is what we know. Take a minute to go through the problem, then we will discuss the solution. I hope the problem statement is clear. So we have been given some properties also. The properties that are given to us are the vapor properties of properties of water in the vapor phase, and properties of this brass material that is used to make up this tube. You can certainly see, you can clearly see what difference this problem has from the previous problems. In previous problems, we just had to worry about the surface temperature of the surface, the temperature of the surface on which this condensation is happening. But here, the driving force that is leading to condensation is the temperature difference between this water and the condensation. So we have to, whenever we write an expression for Q as, say, earlier we used to write Q is equal to H bar into surface area available for heat transfer into the temperature difference, and now instead of this we have a combined heat transfer coefficient and associated area of cross section and associated temperature difference. In that combined heat transfer coefficient, we have to consider the effect of H bar outside, H bar the heat transfer coefficient of the outside surface, heat transfer coefficient associated with the inner surface, and the resistance, conduction resistance associated with this, brass tube. These three things we have to take into account. That is the difference for this problem compared with the previous problem. Shall I proceed for the solution method? And we have been asked to find out the rate of condensation, that is m dot per unit length. That we can do. We can take length to be 1 meter unity, and we can find out the condensation rate per unit length. So if I proceed for the solution methodology, earlier we have already seen that in the first problem we have been writing heat transfer rate as mass flow rate multiplied by the corrected latent heat, right? From this expression we can write mass flow rate as total heat transfer rate divided by corrected latent heat, and what we need to find out is mass flow rate per unit length. For that, what we can do is we can find out heat transfer rate per unit length and divide it by the corrected latent heat. So this is so this is what we have to find out. Okay. the corrected latent heat value is already given to us in the problem. It is given to us that corrected latent heat values 2.2410 kilojoules per kilogram. So we only need to find out the value of total heat transfer rate per unit length of this tube system. Now that total heat transfer rate per unit length, we can express it as a product of a total convection coefficient, say this total U naught by D naught. Yes, this total convection coefficient we can express either in terms of outer diameter. If we express in terms of outer diameter, I can take the area divided by length, since we are taking heat transfer rate per unit length, multiplied by the saturation temperature minus mean temperature of water, because this heat transfer rate is the heat transfer rate associated with the with whatever is appearing between these two temperature regimes. Or alternatively, we can also write it like U naught into pi d, sorry, not U naught, U inner into pi di into T size minus yes, I divided by, because there will be a pi d naught into L here. I took that L on the left hand side, so that it is equal to Q by L. Q by L equal to Q dash equal to, yes, that is right. The left hand side is actually divided by the length. This is heat transfer rate per unit length. Okay, so this is the expression that we need. In this U naught we don't know, we need to find out. Say I am going for this expression on the top. This is the expression that I am going for. U naught I don't know, I have to find out. Pi I know, the diameter of the tube, outer diameter of the tube I know. Saturation temperature is given, yes it is given. Saturation temperature of the vapor is given, 320 Kelvin. Mean temperature of the fluid that is flowing also is given. Okay, so the only quantity that I have to find out is overall heat transfer coefficient. Have you previously done these calculations of finding overall heat transfer coefficient in systems? Either cylindrical systems or okay. So this is a tube. In composite cylinder, yes. Tube with inner diameter of di, outer diameter of do, thermal conductivity of the tube say K, and heat transfer coefficient associated with the inner surface, let it be Hi, and heat transfer coefficient associated with the outer surface, let it be Ho. In such cases, I can write an overall heat transfer coefficient 1 by U naught multiplied by say A naught as, let me start from this outer surface, it is 1 by H naught A naught, right? A naught is the area corresponding to the outer surface, plus if I am writing it for the inner surface, it will be 1 by Hi Ai. But I want to divide and remove A naught from both sides, so I will just multiply and divide by A naught here. Okay, it's a harmful addition, a harmful introduction of A naught on both numerator and denominator, so that I can cancel this A naught from all the denominators. And for this composite cylinder, it would be natural, the corresponding value of resistance would be, the thermal resistance would be ln of the outer outer diameter by inner diameter divided by 2 pi L into thermal conductivity of this tube material, right? Here also let me multiply it by, since I don't have an N0 in denominator that I can cancel with this value, let me just multiply by A0 from both numerator and denominator. So let me just cancel out all these A0 values. Okay, is it okay till now? Yes, okay. So let me rewrite this again. 1 by u naught equal to, here it is just 1 by h naught plus 1 by hi into a outer by a inner. Area of outer by area of inner, it is just like pi d outer into length divided by pi d inner into length. Pi and length will get cancelled out, so it will be just d outer by a ratio of d outer by d inner, right? Plus ln diameter of outer by diameter of inner divided by 2 pi lk. Okay, a0 by 2 pi lk. Let's just calculate what is this a0 by 2 pi lk is. Not a0, sorry, I'm repeatedly saying it a0. This is a outer ao by 2 pi lk. This quantity a outer is just pi d outer into L, the covered surface area that is available for heat transfer. Pi and pi gets cancelled out, L and L gets cancelled. It is just d outer by 2k. So it is just d outer by 2k. Okay, now we have got an expression for the overall heat transfer coefficient, taking into account the contribution from all these heat transfer mechanisms. The value of H outer is known to us, which is 6800 watts per meter square Kelvin. It is known to us. H inner is also known to us. The heat transfer coefficient associated with the inner tube surface wall, that is 5200, 6800 and 5200. HO is 6800, HI is 5200. Outer diameter and inner diameter are known to us. Outer diameter and inner diameter are known to us. And the thermal conductivity of this material. Which material was it? It was brass material with a thermal conductivity of 110 watts per meter Kelvin. Thermal conductivity is also known to us. 110 watts per meter Kelvin. This is not 1 by HO, this is just HO, okay. Watts per meter square Kelvin. This is 5200 watts per meter square Kelvin. And the outer and inner diameters are 19 mm and 16.5 mm. Okay, we have all the quantities in this expression and we can calculate the value of U outer, the overall heat transfer coefficient. So when we calculate this value, I'll just write down the final answer here. I'm getting a value of around 2627. Okay, 2627 with units of watts per meter square Kelvin. Yes. Thank you. Now I can substitute this value directly in this expression to find out the heat transfer rate per unit length. So Q dash equal to this quantity multiplied by pi d outer into T saturation minus T mean. T saturation was 320 Kelvin and T mean was 30 degrees Celsius. T saturation was 320 Kelvin. Yes, thank you. T mean was 303 Kelvin, right? So when I substitute this expression, I will get these values. I will get value for heat transfer rate per unit length, and what value are you getting? I think we will get something around 2665 watts per meter, and we can substitute that value in this expression to get our final mass flow rate per unit length. Mass flow rate of the condensed liquid, condensed vapor per unit length, because we have been given this corrected HFG also as 2410 kilojoules per kilogram. Two 10 kilojoules per kilogram. Okay, so when we substitute just values of this heat transfer rate per these two values, now the heat transfer rate per unit length and HFG, will get the value for mass flow rate. You are getting 1.07. Is there some okay? Note that this is kilojoules. Okay, so just make sure you multiply by 10 power 3 in the denominator. So if you account for that 10 power 3 also, you should get something around mass flow rate is equal to somewhere around 1.11 into 10 to the power minus 3 with units of kilogram per second or kilogram per meter per second. This is mass flow rate per unit length, right? Should it be kilogram per second or kilogram per meter seconds? Can you check? Let's try it here. Q dash by H dash Fg, right? The units for Q dash are watts per meter, that is heat transfer rate per unit length, and the units for H dash Fg are the latent heat is joules per kilogram Kelvin. sorry, kilojoules per kilogram. Mass flow rate per unit length equal to heat transfer rate per unit length divided by latent heat. The units for heat transfer rate per unit length, if I take corresponding units, it's watt per meter. Here it is kilojoules per kilogram or joules per kilogram. So this is equivalent to what is joules per second divided by joules per kilogram. So it will turn out to be kilogram per meter second, right? Is that okay? Okay. So I think this problem was also clear. So this problem involved finding out total convection, total heat transfer coefficient when there were multiple flow surfaces and in between conductive resistances were involved. We found out the total heat transfer coefficient and we substituted that value in the heat transfer rate, and we used that to find out the new mass flow rate. Not new mass flow rate, we used that to find out the mass flow rate of the condensed vapor. So with that, we now solved 3 problems on condensation. Now we will move on to our topic, radiation. In radiation, I think it was mostly definitions and introduction. In the even though we covered 3 lectures for radiation, it was mostly on introducing the radiation concepts and definitions. So we'll cover only one numerical problem in radiation and one small question on radiation. So this is first problem on radiation, problem 4. Let me discuss the problem statement. And let me just read the problem statement for you. A small radiant source A1, which is here, this is an A1 source, emits diffusely with an intensity I1 equal to 1.2 into 10 power 5 watts per meter square steradians. The radiation detector A2, okay, there is this is emitter and this is detector. The radiation detector A2 is aligned normal to the source at a distance of 0.2 meters. So this distance is given to us, distance between source and detector. An opaque screen is positioned midway between A1 and A2. There is an opaque screen here which is positioned midway between the source and detector to prevent radiation from the source reaching the detector directly. So radiation from the source is not allowed to go to the detector directly. An opaque screen is placed here to ensure that. Okay. A1 equal to A2 equal to 1 into 10 power minus 4 meter square. The areas of A1 and A2 are equal. It is given to us, and it is given to us, the value of this area is also given to us. Now the small surface AM, there is a surface AM here at the bottom, is perfectly diffuse mirror that permits radiation emitted from the source to be reflected into the detector. Okay, the radiation emitted from the source is coming to this AM surface and it is getting reflected into the detector. Okay, the angle between these geometries are also given. One of the angles is given to us to be 45 degrees, this theta 1 angle. Now AM is equal to 2 times A2. Okay, the area of AM is also given to us because we know the area of A2 already. It is given to us as A1 is 2 times A2. Calculate the radiant power incident on AM due to emission from the source, that is Q from 1 to M. Calculate the radiant power incident on AM due to emission from the source. Take a minute to go through the problem, understand the geometry, and after that we will discuss the problem statement and solution. I think problem statement is already clear. Just take a minute to go through the problem. After that we will proceed for the solution. Okay, shall we start discussing the solution? I think the geometry is clear. There is an emitter, there is a reflector, and there is a detector. The area of these geometries are given to us: a1 equal to a2 and am is equal to 2 times of a1 or 2 times of a2, and the angle between the normals of a1 and am is given to be 45 degrees. What else? And the distance between a1 and a2 is given to us, and the height at which this a1 center of a1 is also given to us, that is y0 is equal to 0.1 meter. Okay, these values are, this much information is given to us, and we have to find out the radiant power that is incident on am due to emission from source, radiant power incident on this due to emission from a1. Okay, this is what we have to find out. Okay, let's go to our equations. So we have already seen this equation in our lectures. The differential radial power, the spectral value of differential radial power is given by the intensity of spectral intensity of emission, that is I lambda E. Lambda corresponds to a particular wavelength, E corresponds to the emitted radiation, which is a function of wavelength theta and phi multiplied by the differential area, and cos theta multiplied by the solid angle between solid angle to which it is radiating. Okay, now if we integrate this expression, or if we consider this radiation for two non-geometries, we can rewrite this expression as this: the radiation emitted, total radiation emitted from a surface A1 to a surface that is intercepted by a surface AM can be rewritten like this: the intensity, total intensity that is emitted by the surface 1 multiplied by the area of surface 1 multiplied by the cos of the angle between the normals of these two surfaces multiplied by the solid angle between these two surfaces. This is the expression for this, and we have been also given the expression for the solid angle, that is given by the normal area multiplied by the square of the distance, that is am into cos theta in our case, that is the normal area, divided by r square is just x0 square plus y0 square, where x0 is this because r is this, x0 is this, y0 is this distance. It is just Pythagoras theorem. This much is given to us. So it's direct substitution once we know these equations. Scripts are very light and unable to read properly. I will rewrite the expressions here. Yeah. The total radiation that is emitted by 1 and that is intercepted by the surface M is given by the intensity of radiation that is emitted by 1 multiplied by the surface area of 1 multiplied by cos of the angle between normals of these two surfaces multiplied by the solid angle between these two surfaces, and the expression for the solid angle is given by the area that is normal divided by r square or r naught square, which is given by am cos theta m by x naught square plus y naught square. I have just rewritten what we have here in the equations. Is it clear now? Okay. Oops. Okay. So what we are trying to find out is what is the radiation that is emitted by A1 that is being incident on AM. So two equation also please. Actually the second and third equation is given. The top equation I will write it here. dq lambda is given by I lambda E, which is already a function of wavelength theta and phi, multiplied by the differential area of the emitter, multiplied by cos theta, multiplied by the differential solid angle. That is the top equation. Okay, now let's proceed to find out the solid angle between geometries A1 and AM. Solid angle is given by AM. We already know AM is 2 times A1 and A1 is 1 into 10 to the power minus 4 meter square. So AM is 2 into 10 to the power minus 4 meter square. And cos into theta m. Which one is theta m? Theta m is this one, the angle between the normal to AM and the line joining centers of these two surfaces. Since this is like this forms an isosceles triangle, so and since theta 1 is already given to us as 45 degrees, and since this is 90 degrees, we can take theta m to be 45 degrees. So this expression will turn out to be cos theta m equal to cos 45 degree divided by x naught square plus y naught square. What are the values of x naught and y naught? Y naught we already know it is 0.1 meters, and x naught, since this is an isosceles triangle, x naught is also 0.1 meters. So this will be 0.1 square plus 0.1 square. What is the solid angle that we are getting? Make sure 7.07 10 to the power minus 3. You substituted the angles correctly, right? Radians and degrees. Yes. Okay, what value were you getting? 7.07 to 10 to the power minus 3 radians. Yes. Good. The unit for solid angle is radians. You appropriately mentioned that. 7.07 to 10 to the power minus 3 radians. So 7.07 into 10 to the power minus 3 radians. Okay. This is the solid angle. Now we can directly go substitute this value in the first equation to get the total radiation power that is emitted by 1 and that is intercepted by the surface M. The value for I1, that is the intensity of radiation emission from surface 1, is 1.2 into 10 power 5 watts per meter square steradian. 1.2 into 10 power 5. Multiplied by A1. A1 we already know it is 1 into 10 power minus 4 and cos theta 1. Theta 1 we already know that it is 45 degrees. Multiplied by the solid angle, that is 7.07 into 10 power minus 3. Okay. This is the radiation that is emitted from surface 1 and that is incident on surface M. If we calculate this value, 60 units, 60 milliwatts. Okay, yeah, it would be a small value, 60 milliwatts or 0.06 watts, right? Yeah, yes, 0.06 watts, yes. That was a small problem on radiation. Since we have not formally started, we just 0.0599, yeah, close to 0.06 watts. Yes, thank you. In the radiation, even though we covered 3 lectures, we were formally getting introduced to the different definitions of radiation, and I think the next week and maybe the week after that, I'm not sure, next week anyway would be radiation, completely radiation. Maybe the week after, it could span to the week after that also. So we will get to see more on these radiation problems in the coming lectures. But before finishing this problem solving session, I will just discuss a small problem statement also, that is problem 5. In this we are being asked to identify the incorrect statement. Okay, 2 statements are given to us and we are being asked which of them are wrong. Let's check if these statements are right or wrong. Okay, statement X: the radiation intensity is independent of the angle of emission. Is this statement right or wrong? Radiation intensity is wrong, yes. If the radiation intensity is independent of the angle of emission, what would be called for such surfaces or such type of emissions? We are talking about the angle of emission only. If there is a surface, the intensity at which the radiation is emitted, does it depend on the angle of emission? This radiation emitted in this angle and radiation emitted in this angle, do they always need to be equal? That is the first thing that we are being asked. We are also discussing that this radiation depends on the surface structure, the surface roughness of these structures. For it to be equal, we call such an emitter as diffuse emitter. Only in diffuse emitter characteristics, this dependency on angle would be, we can neglect. We can say that in diffuse emitters, this radiation intensity would be independent of angle of emission, but in all other cases we can make such a generalized statement. So if when we make a generalized statement like this, it is a wrong statement. Okay, now let's go to the second statement. Radiosity is essentially the reflected radiation from a surface at a certain wavelength. Radiosity. Okay, one of you is saying it is wrong, and one of you is saying it is right. What is the definition for radiosity? If there is a surface and if there is some incident radiation, radiosity refers to, let me check your definition. You are saying radiosity refers to the total reflected radiation, both specular and diffuse, from the surface at a specific wavelength. Is it only the reflected radiation? Suppose there is some incident radiation. Yes, some part of this radiation could be reflected. It is reflected radiation. This is, say, incident radiation. This is reflected radiation. Apart from this, the surface itself emits some radiation of its own. Apart from the reflection, the surface emits some other radiation also. So the radiosity we represent using J, right? Radiosity, we say it has a sum of this reflected radiation plus emitted radiation. So it is not only the reflected radiation, but a sum of reflected plus the emission from the surface itself. So this statement is also wrong. It is partly correct, but it is not fully correct. So this statement is also wrong. Okay, yeah. That's all I had for today, because we had not gone deep into the radiations. I have not included more problems on radiation, but next week I think it will be completely a session on radiation, so we can look more into more and more involved radiation problems in the next week. If there is nothing else, I think we would close the session here, if everyone is okay with it. Shall we close the session? Thank you. Oh, thank you for attending the session. Yeah, thank you for attending the session, and we'll see you next week for the next week's session. Thank you.